Thank you everybody for being here and hanging around, although I guess free beer and food helps attract an audience, so maybe I'll try that myself more often. First of 3 talks, which I think is supposed to narrow in from high level, what is organic matter, right down to some of the learnings from the cover crops trials that we were wandering around this morning that Tom's been looking after. I'll start with some acknowledgements, mainly because you'll probably be fed up of hearing me by the time I finish speaking. Firstly, most of the research I've done was funded by other people, particularly through National Lawn Care Programme, GRDC and the CRDC, so cotton. Importantly, most of the work that I present wouldn't have been done without a lot of people on the screen behind me. Jeff Bollock is a face you probably mostly recognise, and probably half these slides were his at some point. Lynn MacDonald, another team leader in our group in Adelaide. Sanani, who is based in Canberra. 2 ex-postdocs of mine, Jess Anokovic and Courtney Creamer. And none of them would have had in day 3 either without our lab staff. So I just want to get that across, that I stand on the shoulders of a lot of other people to be able to present some of this to you. So first of all, try a little bit of deconvolution. Soil organic matter, soil organic carbon. We had a nice little technical conversation about inorganic carbon earlier today, which I'll touch on as well. So soil organic matter, if you're measuring it directly of sorts, you basically set it on fire and weigh what was left. Not so many people do this that often anymore in analytical labs. Mainly because it implicitly includes carbon, but all this other stuff too. Oxygen and hydrogen that contribute to it being there in the first place, and then there's other nutrients in there as well. So there is a correction factor between the two that's a bit woolly around the edges, assuming that stays the same for all organic matter, which it more or less doesn't. But yes, it's if you're talking about organic matter, it's more than just the carbon, and that's important if we're thinking about carbon sequestration, for instance. So organic carbon, on the other hand, really is just the carbon that's in that. And again, we talked about this briefly in the field. These days, it is usually a direct elemental measurement by high temperature combustion, or LECO. It can be done by wet chemistry, Walkley Black. Carbonate is a bit of an issue as being discussed. Ultimately, most of these methods, apart from Walkley Black, just measure total carbon. So if you've got carbonate in there, you're going to get some fairly misleading results if you're thinking about organic carbon. But importantly, it is just carbon, at least, as opposed to organic matter, which is everything. Now, I can guarantee you in this talk, I will probably interchangeably use soil organic matter and soil organic carbon. Most of us do, and don't realise we're doing it until we realise just how much confusion we're causing for the people who do try to differentiate the two. So why are we interested in soil organic carbon? Well, the interesting thing to start with is that, well, what was it we were talking about, one of the soils? 0.3%? So 99.7% of it's something else. Why do we care about the carbon? It's a very small component in most soils, with the exception of peats. Even a high carbon soil, something like irrigated dairy down in the lower southeast, would only be 6-7%, and that's just in the topsoil. It decreases quite rapidly further down. So why do we care about such a small component? Well, first of all, it's an integrator across soil type and climate. Management can change it also. It's normally the third of those 3, unless you're really doing something fairly outlandish, irrigation being the most obvious one. If you're certainly irrigated pasture, can have really high levels of carbon relative to the natural environment around there. But it is normally, if you take it at the national level, you see quite clearly, we have lots of carbon where it's wet and not so much where it's dry. And within that, it is moderated primarily by soil type within that. It is susceptible to loss too, as we know. One of the reasons we talk about it so much, though, is because in a lot of soils, it's doing quite a lot. And it does different things in different soils. So in sandy soils, we'd expect it to be providing the bulk of the cation exchange capacity that soil might be providing to moderate the availability of nutrients, retain nutrients and release them. It obviously, depending on how clay dominated or sand dominated the soil is, it's pretty important for soil structure. At either end of that spectrum, its impact is really lost relative to that of the mineral matrix. Clearly with no carbon, microbes have nothing to eat, and you have no microbes. Likewise, it's pretty important in all soils for the provision of nutrients, and particularly in sandy soils, it's the main sponge which holds your water. Obviously, its influence tails off in clayier soils as the clay takes over. And organic carbon, is it the only carbon? No. This is where we have fun, particularly in South Australia. Our state soil is the calcareous soil. And actually, depending on how you measure it, there's this quite off-quoted figure that solid organic carbon is the largest terrestrial carbon stock. There's a bit of contention around that, because within error of measurement or estimation, you could also argue that soil inorganic carbon is the largest terrestrial carbon stock. And particularly in South Australia, there's an awful lot of it. In calcareous soils, indeed we were talking about some of my problematic soils on the Lower York Peninsula, it can make up pretty much all of the soil full stop, never mind all the carbon. But it is present in other soils from around pH 7.5 and onwards, and we were seeing a small fizz even at the surface in the soils we were looking at today with Brian. We do consider it separately. There's a question as to whether or not, whilst it needs to be considered separately, whether or not it should just be ignored, which is what it currently is when it comes to carbon sequestration. The main reason it's ignored is it's presumed not really to do that much, to be fairly inert, sits there, biological processes don't add to it, nor do they subtract from it. Neither of those are quite true, and it's a bit of a blind spot in soil carbon research more generally that really does need a bit more attention. Something else I want to cover. We talked, again, in the pit about percentages of carbon. But if we're wanting to think about carbon sequestration and generating carbon credits, offsetting carbon, well, that's measured in tonnes, not percents. So we need to know about bulk density and calculate carbon stocks. And the reason why this gets everybody so het up, we're used to converting by rule of thumb measures from milligrams per kilogram of nitrate through to kilograms per hectare of nitrogen that's available. It doesn't matter whether or not that's 10 or 20 kilos out, roughly in the grand scheme of things. But if you're trading soil carbon, you need to know how much you actually have there and how much you've actually sold, which is why this becomes much more complex than it first appears. Because if you're taking a 30 centimetre core and you take 31 centimetres, well, that's quite a bit of error right there. Maybe you only took 29 next time. You've lost carbon. No, you haven't. You just haven't actually taken quite as much soil out the ground. Gravel, all those other bits of fun really cause problems. And the interesting thing is, and this is a little bit of work that Jeff pulled together from SCARP, we had a look at just where this error lies in calculating a carbon stock. It's 10% error in that number. We can measure very accurately the concentration of carbon in whatever you put in the instrument. The error is not in the measurement. A little bit of error in measuring moisture content because it's done gravimetrically. Most of your error is coming from actually taking the sample and subtracting the gravel from it, which is where it comes back to measuring stocks of soil carbon. It really comes down to how you sample in the first place. Actually, the lab, it's not a lab problem at all. It really never has been for a well-run lab. And it's the need to actually have it back as a true stock rather than roughly 50 kilos per hectare or roughly 70 kilos per hectare when you're thinking about nitrogen stocks and thinking about fertilizer rates. Because this stuff has monetary value, that's more of a problem. So another thing I wanted to cover about organic carbon is whether or not, again, we've talked about carbon. Early this morning, Jeremy was talking about labile and more recalcitrant carbon. So no, carbon isn't all the same. First of all, and I did joke at one point, certainly the buried almonds that we were recovering, for instance, they're not technical soil carbon at all. They're buried plant residues for fairly arbitrary reasons. We've always counted anything greater than 2 millimetres as not being soil in the first place. mainly because we count it as gravel for anything that isn't carbon, and therefore we assume large bits of plant material are also not yet soil. So we discount them entirely, and certainly we discount the stuff that's on the surface. But there is a continuum, and basically as you go down this profile of this sort of continuum of carbonaceous material, carbohydrates decrease, the carbon to nutrient ratio decreases, and the resistance to further decomposition increases. And this is on a sort of continuum. Down into particulate carbon, so we actually, across carbon accounting framework within Australia, within CSIRO, within SCARP, and within quite a lot of other research areas now, we're pretty comfortable with having 3 types of carbon that we can define quite clearly from a functional perspective, and we can separate them in a lab and actually get meaningfully different things. It's very easy to come up with lots of differences that are arbitrary and operational, but we actually can assert fairly clear meaning to particulate organic carbon, humus-like carbon, and the further joker in the pike, the resistant or pyrolytic organic carbon. So this is the charcoal. And the reason I've left that till last is that whilst these 4 form a continuum, there is basically a massive step between the humus-like carbon and the resistant carbon that really behaves totally differently. It is extremely resistant to decomposition. It actually almost behaves a bit more like a clay, I would say. It's basically clay made out of carbon rather than actually being organic carbon and functioning and delivering a lot of those services that I've just talked about. And yeah, in some regards it poses almost the same problem for analysis as carbonate, except for the fact we can't make it go away with a little bit of acid. It's interesting that in the sort of the Green Book Bible for soil analysis, the actual approved method for measuring organic carbon has a step of manually trying to remove particles of charcoal that are there, which is a bit worrying because it brings in all sorts of horrific operator error into it, but the fact that it's recognised, there's just no fix for it. The reason I separate them out this way is because they do, not only are they chemically different, they're physically different. If you look at them down in an electron microscope, there's particulate carbon, you can still make out the cellular structure of plant. It still looks like plant material that is decomposing. The humus-like carbon, and note the massively different smaller scale bar on this one, these are basically bits of dead microbe. This is waxy substances. They're the bits that are actually holding the soil together. And the reason that a lot of that is stable isn't that it's that chemically recalcitrant. It's actually mostly lipids, and lipids will break down happily enough. It's that they're stuck to clay particles, they're protected from decomposition, and because they're fairly hydrophobic, it's actually much harder for microbes to break down. The charcoal stuff really does look exactly what you like charcoal. It's basically frozen in time plant material that's been chemically changed through pyrolysis. And chemically, they look quite different as well. So these are NMR spectra, the main instrument that we use for looking at the stability of carbon. The particulate carbon, this peak here is the carbohydrate peak, really high, really dominated by that. If you look at the humus-like carbon, they're either similar or actually with a higher alkyl peak, so this is more the aliphatics, the fatty components. Again, neither of those, though, are actually that recalcitrant if you had them without any protection from the clay material in soil. It's one of the reasons that sandy soils struggle to retain carbon, because there just isn't the surface area for these things to stick to. The resistant or charcoal-like component, on the other hand, is entirely different. So, these are different, and if you can interpret an NMR spectra, you can see that they're fundamentally quite different. That's just a totally different substance entirely, and that's why it's an interesting thing to be dealing with in these systems. All right, so why do we care about that? Well, this has to be the favourite graph my favourite graph of Jeff's, because it's utterly useless. 6 soils from New South Wales, from SCARP, they've all got different concentrations of carbon in them. Great. That tells you absolutely nothing at all. But if you know about the fractions in them, you can start not only having a guess at what the management might have been there, what environment they come from, but also how vulnerable that carbon might be to loss. If you take this soil and this soil, for instance, they have pretty much the same amount of resistant carbon, pretty much the same amount of humus-like carbon. very different amounts of particulate carbon. These two could be neighbouring paddocks, that one's irrigated and that one's not. Could be, I don't know. But those are the sorts of things you can start saying about them. And because we know that these components of carbon have very different residence times, from years to a decade for the particulate, up to centuries for the humus-like, and then millennia for the charcoal-resistant fraction, we can actually have a good go at having a guess as to how stable this stuff would be with the practice change. Now, clearly, if you're in a hot, arid environment and you stop irrigating, that could happen quite quickly to that soil. Whereas conversely, that one's got almost nowhere to go. That is much less likely to be losing carbon. And this is that same map that I showed before, but this time now with that vulnerability layer laid over it. Now, it's interesting that if you look at the, yes, I do have it, sorry. So the original one with the carbon stocks alone, you can see the mallee there, low carbon. And all the other, and the wetter areas with the higher carbon, and then the arid interior. You can see the mallee here too. So this is about the only spot in the country where you have both low carbon and what carbon is there is still pretty vulnerable to loss. So this is useful information. You'd expect where there was an awful lot of carbon, so Southern Vic, Gippsland, Tassie, that yes, if it stops raining there, and with climate change, certainly rainfall patterns will change, that those large amounts of carbon may be vulnerable to loss. But the mallee in particular is peculiar in having little carbon, and even though there's not much carbon there, what little there is there is still particularly vulnerable to further loss. Worth bearing in mind. So one thing I wanted to cover as well was where these things are coming and going from. And I brought nitrogen into the equation here, as discussed earlier. You don't have, and of course with the differentiation between organic carbon and organic matter, you can't have organic carbon without having some nitrogen, and indeed phosphorus and sulfur also. And with the exception of bringing in inputs, and this is one of the reasons for focusing on cover crops, the main source of carbon in soil is coming in from the plant that's growing there. You can grow more plant, or you can grow plants at different times, but ultimately one of the ways to get more carbon into the system is to, in fact the only way to bring carbon into the system that's not come from another system is to grow it in situ. Fertiliser, on the other hand, of course, we know how much we're applying. And the main reason I put this slide together and show it quite often to growers is growers know how much fertiliser they apply. You know, we've talked in the paddock, yes, you're putting 200 kilos of N and 120 of potassium. You know that, you bought it, you know how much it cost, you know how much you've applied. Most people wouldn't have the foggiest how much carbon their plants are adding to the system. And this is why I want to actually just raise this, that the main source of carbon in these systems is what you're growing in the first place, unless you're bringing huge amounts of external organic amendments. Now, I discussed about building carbon and its losses. This is data from the classic long-term trial in Rothamsted. And one of the problems is that yes, you can build carbon, and this is manure, so they've added lots of external inputs year after year from the 1850s onwards. Then around 1870 they stopped applying it, and as quickly as they built it, it decreased again. So if you're bringing carbon in above a threshold or even towards a threshold, if you stop doing it, there's practice change, it will go away again almost as quickly as you brought it. And the other thing to note here is that they carried on applying the same amount of manure, but over time, reaching a new plateau, no matter how much more they added, most of that carbon got lost again, presumably because the clay was saturated and you basically reached the upper limit that that soil can hold. Now, there are potential ways to modify that to some extent. Biochars, adding clays, so in a sandy soil, spading and bringing up clay would theoretically change that to some extent, but ultimately you will reach a carrying capacity upon which you can add no more carbon. And for these sandy soils, that is probably very, very low. So just touching briefly on nutrients, as I'd said, there's all this other stuff that makes up organic matter, and apart from diamonds and charcoal, there's no carbon that is just carbon. So you're basically not going to be able to build carbon without nutrients. And one of the reasons, of course, that we want to build carbon is because it forms a buffer of nutrients that it can supply to the crop and Typically throughout the growing season, nutrients are mineralising at roughly the same sort of rate as a plant is trying to take them up. So it's a very effective slow release fertiliser if it's managed appropriately. It is moderated by a lot of other factors, and they're not perfectly coupled, these rates, but it's a lot better than most fancy slow release fertiliser you might be trying to buy. This is data from one of our colleagues at Queensland Department of Environment, Diane Allen. This is from sugarcane, and she did a great study a couple of years ago now, and basically showed a really good relationship between organic carbon, particularly as measured as active carbon, as a simple respiration measurement, and the amount of N released through mineralisation assay over a year. So these things can be fairly well coupled. There is a relationship between the amount of carbon you have that is being used and the amount of nitrogen that is mineralised and available for plant growth. And we did touch on this a little bit in the paddock. It's not such an issue in, I don't think, in irrigated hort as it is in broadacre cropping. The reason I want to go over it anyway is because, of course, a lot of the general view is that agriculture applies too much nitrogen, and I tend to agree with that in places and greatly disagree with it in others. Broadacre ag in Australia, I would certainly disagree with it. This is data from a study that Rob Norton did for GRDC a few years ago across 125 different paddocks across southern Australia. Almost every single one of them is nitrogen negative. So more nitrogen is being taken off in the grain than is being applied as fertiliser. That doesn't even account for any nitrogen that's being lost. That's assuming that all the fertiliser you applied went into the grain, which it almost certainly is not. So the only other place there's nitrogen coming from is your organic matter. So it's little wonder that organic matter, particularly in dryling grains, is going backwards, because we have a system that's so tightly tuned to limit the amount of nitrogen that's applied. It's being mined. You're mining nitrogen in much the same way a miner would mine copper. And there are situations that this is appropriate, but you need to know you're doing it. Think of it as an overdraft at the bank. It's fine, you go and see the bank manager and arrange an overdraft or a loan. But if you systematically are taking out $100 more than you earn every week and don't have a conversation with the bank manager, sooner or later they'll come and have a conversation with you. And the same effectively is a cliff that a lot of Australian soils may already be at or are certainly driving towards as a result of not actually applying enough fertiliser rather than applying too much. And I think this is just driven from, we all know, see the pictures of rivers with eutrophication. I talk about the Great Barrier Reef, and certainly sugarcane is an area where this probably doesn't apply to, but certainly broadacre grains, simple mass balance of N in versus N out gets you a pretty scary picture. So to build organic carbon, we need nutrients. Ultimately, depending on the source of organic matter inputs, they may be slow to decompose, but doesn't necessarily mean that they're stable in the long term. Because again, I'm just cutting back to that idea, what really confers stability on organic matter is its association with clay particles, formation of aggregates, etc. Just because it's slightly more chemically inert, I mean, fragments of wood would break down in 5 or 6 years rather than 1 year for legume stubble. That's 5 or 6 years, it's not centuries. For it to be stabilised over that longer term, it needs that association with the clay materials. So quickly wrapping up some conclusions. Organic matter is complex, but it can be systematically looked at and it's not too hard. It's basically, you've got 3 forms that behave. One turns over quickly, one turns over slowly, and one effectively doesn't turn over at all. And if you know a little about those 3 things, as rules of thumb, you know a lot more about it than just having a percent number overall. There are carrying capacities for systems, which you can modify, like I say, irrigate in Australia, mostly water limited, so if you're irrigating, you can probably build some more, but only to some upper extent, and in certainly our sandy mallee soils, that upper extent is probably actually still pretty low. And what you build there would be incredibly vulnerable to loss due to practice change in the future. Organic matter is also a source of nutrients, but the flip side is you need nutrients to build it in the first place. And again, going back to dryland grains, We all know how much fertiliser costs at the moment. There's a lot of squealing about the idea that you've got people like me advocating for applying more. Well, what's the value of the nutrients you've used for the last decade that's come out of the soil? They're not going to come forever. There are opportunities to both build or lose carbon in agricultural soils. I'm certainly not of the viewpoint that it's hopeless and we can't do this. There are certainly strategies in place that can build carbon. I would say there are strategies in place that can still build carbon in the systems we've been looking at today. Amounts, yes, probably not as much as some people would like, but it can be done. But there is the vulnerability to loss. And one thing I haven't really talked about much, but does worry me a little bit, is the nitrous oxide side of things. If we've got systems that got slightly more nitrogen in, more active systems, and they're producing nitrous oxide, the greenhouse gas equivalent, the CO2 equivalence for nitrous oxide is 320 times as much, as potent as carbon dioxide. So it really doesn't take much to offset what little carbon you may have built if you do it poorly. And on that cheery note, I'll leave you with a sunflower.